Calculus 2, Section 7.7, Hyperbolic Functions. What are hyperbolic functions anyway? Well, in a short definition, they combine e to the x and e to the negative x in different ways. And you might say, well, that's big. Why don't we just use e to the x and e to the negative x? Those, remember, those natural log exponentials and lead to logarithms too. So I've never heard of hyperbolic functions being used for anything. But they do simplify a lot of mathematical expressions. And they occur in many, many math applications. What you should do is go online and just say applications of hyperbolic functions or something like that. And what you'll find is a hanging wire. It'll describe how a wire hangs. That's not a quadratic necessarily. It's better to do it with these exponential functions. It works with Lorenz Transforms. The Lorenz Transforms is something that you might look at later on. It's upper level mathematics. Sort of interesting. I don't understand it completely myself. They do zero mean curvature for surfaces. That's the minimal surface. You might learn that in perhaps topology and stuff like that. Mercator map projections. Perhaps graph theory, but probably not. That uses the inverse hyperbolic tangent, using also as an argument for that, the hyperbolic sine of the latitude. That's sort of cool. Velocity, if you like physics, velocity in special relativity is not linear, but it becomes linear when you express it in terms of the hyperbolic tangent. The dome of St. Paul's Cathedral in England, which really means, I guess, if you want to do some architecture, things like that, you might be using this. The hanging wire, the dome in St. Paul's Cathedral. A lot of this stuff that seems sort of interesting when you go online and just say hyperbolic functions applications. So, what are these things defined as? Well, let's see here. Sine h of x. We can put parentheses. We usually leave that off, just like for sine x. We're going to call this sinh, though. Like, it's easy. That's a sinh. Depends upon what country you're from, how you might pronounce this. I guess in England they call this shine. I'm not sure why they moved the h over here, and cinch doesn't make a whole lot of sense with the ch, but that's what we usually call it here. Depends upon where you're at. You might want to make sure you pronounce it correctly. This is, when we talk about combinations of this e to the x and e to the negative x, is one of the foundations, e to the x minus e to the negative x over 2. That's how it's defined. The hyperbolic cosine, or Cosh of x, and I probably won't use these parentheses unless I feel it's necessary. Now, sometimes they call it Cosh. I call it Cosh. Some people use the C-O-S-H as Cosh. In England, they call it Cosh. So maybe this is one time I'd use the English pronunciation. It all depends. Just be aware that somebody might pronounce it differently than you do. The only difference between sinh and Cosh is that there's addition in the numerator instead of subtraction. Of course, the hyperbolic tangent, now some of they call it tanh x. That would be the sinh over the Cosh, which would be the e to the x minus e to the negative x over 2. But then if you divide by this Cosh, you divide by the 2 also. They cancel. It's e to the x minus e to the negative x over e to the x plus e to the negative x. The sech, now some of them call this sech, some call it sech, but I'll probably call it sech. That's what I'm used to. This is just the reciprocal of the cosh. 2 over e to the x plus e to the negative x. The coth or coth, depending upon where you're from, of x is the reciprocal of the tang. It is the addition over the subtraction instead of that opposite. The cosech, which is sort of different, I guess, cosecant, cosech, CSCH, and that's the reciprocal of the the sinh. 2 over e to the x minus e to the negative x. So now, what about the graphs of these things? Well, on the TI calculator, you might have them available in the newer operating systems that are easier to get than these, but let me clear this out. They are at least in the catalog. If you want to graph the sinh, second 0 gets you to the catalog. Oh, make sure you're in the y1 equals also. Notice you're in alpha mode, so you press the S to get down to those S's quickly, and then you look down with the arrow keys until you see there's the sine, the inverse sine, the sinh, and the inverse sinh. So I'm going to do sinh x. Now you can do a zoom standard, and it's not too bad. Sinh x looks sort of like a cubic. So that's one way to get this, or you could put in the parenthesis e to the x second ln with an x minus e to the negative x second ln negative negation by the enter key x. Close that, close the numerator, divided by the denominator's 2, and then when you graph it, you get the same thing. So these definitions, but it's a lot easier maybe to find the sinh, and I think the new operating system allows you to get there much more quickly. So the sinh looks like a cubic. If we go to y equals and clear that out, you can go second catalog. The cosh is in the C's. We're in alpha mode. So click on the C, go down until you see CCOSH X. And this looks pretty much like a quadratic, but it's moved up 1. Interesting. When you put a plus here instead, it's usually done something like this. Otherwise, it's always positive. That makes sense, though. The exponential is always positive, and when you put a plus, you're going to get everything positive. The hyperbolic tangent, clear this out, and do a second catalog. You're in alpha mode, so you go to the T's, the inverse tangent, the hyperbolic tangent of x. And graphing that is more like a cube root. It only goes up to 1 and down to a negative 1. It's got an asymptote. So you can get those easily. They are on, let's see, page 426 of our textbook if you need those. But we're not going to focus on those a lot. In fact, I'm not going to make you memorize all these. We'll use them enough so the sine, cosine, and tangent will all you'll remember those easily enough. And because the sech is the reciprocal of the cosh, the cosech is the reciprocal of the sinh, and the coth is the reciprocal of the tanh, then you'll be able to do some of these things exactly like you would if you had just the regular trig functions. But be careful. The IDs are different. They're close, and close enough to maybe confuse you. And once again, I'll allow you to be able to use your book when you need these. What would you guess? The cosh squared x minus the sinh squared x, squared x would equal, well, this was our cosine, I guess cosine squared minus sine squared was the cosine of 2x. In this case, it's like the cosine squared plus sine squared. You got to have the cosine first. What is the cosine squared plus sine squared? Well, that's where it sort of switches. The cosh squared x plus sinh squared x is the cosh of 2x. So these have switched essentially. The cosh of 2x, cosh squared x you can write it by subtracting these things and stuff, but you also have cosh 2x plus 1 over 2. So you just got to be careful. It doesn't behave the same way as we're used to. If you need an identity to rename things, let's see, the tanh squared of x. We used to say tangent squared plus 1 equals secant squared. Well, tangent squared equals 1 minus secant squared, so that's where it's going to be confusing. This would have been a secant squared minus 1. Or now it's tangent squared minus 1 equals a negative secant squared. Or maybe it's 1 minus tangent squared equals secant squared. Oh my gosh. It can get confusing. Look them up to make sure. I forget which page they're on. Okay. But you might be saying, what are the derivatives? So here they are, the derivatives of hyperbolic functions. The derivative of sinh u is nicely the same, cosh u du dx. The derivative of cosh u is even nice. It is sinh u du dx. The derivative of tangent u, same idea, sech squared u du dx. The derivative of coth is a negative cosech squared u du dx. So those are similar, although derivative of cosh is positive sinh. These have worked sort of the same. The tanh and the coth are the same. You're getting something similar, but not quite the same for the sech, the derivative of sech u. We would hope it would be sech tanh, but it's a negative. Sech u tanh u du dx. So it's got a negative. And for the cosech, it is cosech cotanth, and it is negative. Cosech u coth u du dx. So you just have to be careful of these negatives. And I will be allowing you to use these tables and books, maybe not books, but at least a sheet that would give you all these. It's really hard to memorize these, in my opinion, unless you use them an awful lot. And we're not going to use them enough to really gain that. I just want you to know, if you needed to, you could say to yourself, gosh, is that cinch or is it the negative cinch? Now I forget if we put a negative on there or not. Look it up, make sure. The integrals, I'm not going to go through the integrals because all they've done is take the integral of the right side to get the left. And if the right side has a negative, they put the negative on the left. So all of these are really, to find the integral, you use the right side. And once again, if you have them written down, you can, I guess, figure those out pretty easily. So let us put down, here if we can squeeze in a different color, the problem that uses these. It is number 8. We want to find, let's see, rewrite this Cosh and cinch in terms of the exponential function. So the Cosh of 3x minus the cinch of 3x. Well, if I rewrite that, the Cosh, or whatever the argument in, becomes the exponent for that. That's that e to the 3x plus, for the Cosh, e to the negative 3x over 2 minus e to the 3x minus e to the negative 3x over 2. The Cosh minus the cinch with the 3 x's. But now we can put these over a common denominator. It's e to the 3x plus e to the negative 3x minus e to the 3x plus e to the negative 3x over 2. And so these e to the 3x's cancel, but the e to the negative 3x's don't. You get 2 e to the negative 3x's over 2, and the 2's cancel, so you just get e to the negative 3x. So all that comes down to this 1. You could do the reciprocal, 1 over e to the 3x if you wanted. So that's what these problems are going to be like. Let's do one where you take the derivative. This is number 18. Find the derivative given y equals ln Cosh z. So what is dy dz? Because we're doing this in terms of z. Well, the derivative of the natural log is 1 over its argument, Cosh z, times, now we need the derivative of Cosh z. Let's see, the derivative of the Cosh was the cinch of z, dz dz. So this is really just the cinch of z over the Cosh. And many times in the book, at least, we'll take these. That's a correct answer, except the cinch over the Cosh is the tanh of z. So the book's going to take it a little further. If you need to match the book, you might need to do some algebra or hyperbolic trig identities. Now we're also, the one reason I'm going to let you use the a sheet of those rules for finding derivatives is because we're going to go right ahead and figure out the inverse hyperbolic functions and their derivatives. So now you get 6 more of these. You got 12 things to worry about in just this section. If you have the inverse hyperbolic function, say the sinh inverse of x. That can be rewritten using the same things we've done before. The sinh of y is equal to x. And just like before, the graphs, if they use the y equals x line, so if the sinh looks like the cubic, the inverse sinh looks sort of like the cube root. And these are the inverse functions because there's still that symmetry with respect to the y equals x line. All of these are that way. The Cosh inverse means that the cosh of y equals x, changing from one form to the other. If you'll remember, the cosh looks sort of like a parabola. And in order to make this one-to-one so we can get an inverse, we're going to chop off this left side. So when we want the inverse, instead of it being at 0, 1, it'll be 1, 0, and it'll do something like this, sort of like x squared and the square root of x. So a lot of these you can think of similarly. The inverse tangent is going to use sort of like the cube root rather. But let's look at our sech. The inverse sech of x means the sech of y is equal to x. If you remember, the sech of y goes through 1 here and does something like this. It is also not 1-to-1, so they're going to chop off this part and then use this. If you can think of that y equals x line, this will start here and do one of those things. So these are sort of like the trig function where you're going to cut some stuff off. But they don't look like the trig functions because they're not periodic like the trig functions. So be a little careful. We need it 1-to-1, and sometimes that's not possible. Some important identities to recognize, and this happened with the trig functions too, when you wanted to rewrite something. If you have the sech inverse of x, how can you rewrite that with the cosh? Well, it's not 1 over sech inverse. That's true for the hyperbolic, but not the inverse. It is the cosh of 1 over x, inverse cosh of 1 over x. So you don't invert the function, you invert the argument, just like you did before. The coth inverse of x is the same as not 1 over the tangent, but the tang inverse of 1 over. So just remember that's happened in trig also. So you might say, okay, what are the derivatives of this? Derivatives of the inverse hyperbolic functions. Well, it's a lot to write. So, what is the derivative of inverse sinh? Sinh inverse, we'll use a u. What is the derivative of the inverse cosh? What is the derivative of the inverse tang? What is the derivative of the inverse sech. Oops, not equals, not yet. The derivative of the inverse cosech and the derivative of the inverse coth. Let me change colors. So, these may look familiar. 1 over square root 1 plus u squared du dx. That's the sinh, inverse sinh. Now, this is where it gets a little, well, I guess, 1 over the square root u squared minus 1 du dx. For the tanh, similar, but it's easy to get confused, 1 minus u squared du dx. For the coth, interesting, 1 over 1 minus u squared du dx. The same? Yep. The sech, negative 1 over u, no absolute value necessary, and 1 minus u squared du dx. And negative 1 over absolute value necessary, square root 1 plus u squared du dx. So the sinh and the cosinh inverse, the cosh and the sech inverse, they sort of go together. But you don't need this absolute value. The integrals, once again, are just the opposite of that. So these that are, the same, you probably should use the tanh instead of the coth inverse. Okay. Let me go, even though, let's see, can I fit it on here? Should I try to fit it on here? This is number 28. We want to find, given y equals the quantity theta squared plus 2 theta times the tanh inverse of theta plus 1. Find the derivative. I might have to start here. dy d theta, it's the first, right, times the derivative of the second. Now, remember the derivative of the tanh is 1 over 1 minus u squared. So this is, can I squeeze it in here? 1 over 1 minus u is theta plus 1 squared. Plus the derivative of the first, 2 theta plus 2 times the second, inverse tangent or inverse tanh of theta plus 1. So, see if I can squeeze this in. Now, what you're going to find here is this is theta squared plus 2 theta. When you square this, you're going to get theta squared plus 2 theta plus 1. But then you're going to subtract that. So it's a negative theta squared. I'm sorry. The 1's cancel, but it's going to be a negative quantity theta squared plus 2 theta. So this theta squared plus 2 theta over the negative theta squared plus 2 theta, because the 1's canceled, it's going to just be 1. Plus, well, now you've got this thing, which you really can't do too much with, except for write it out. 2 theta plus 2, inverse tangent, theta plus 1, close the parentheses. So this is our answer. But it's important to recognize this. Theta squared plus 2 theta. This is a theta squared plus 2 theta plus 1. Pull out the 1 so you can subtract it from this 1. You get a negative theta squared plus 2 theta. Sort of neat. Need some algebra skills for this stuff. Let's do number 36. Change colors. You're given y equals Cosh inverse of the secant of x. Find dy dx. So, the Cosh inverse, let's see if I can remember that. It's 1 over the square root of u squared minus 1, and u squared is the secant. U is the secant, so secant x squared minus 1 times the derivative of the secant, which is secant x tangent x. Well, secant squared x minus 1, remember your trig identities, that's the square root of tangent squared x times secant x tangent x. Well, hold it. This is just 1 over the absolute value of the tangent times secant x tangent x. Now, these are going to cancel. The big question is, how is that absolute value going to affect all this? Because the secant all by itself goes on forever. But if the tangent of x is restricted to, let's see, this tangent, we'll put it over here. I have a vertical asymptote of pi over 2, and another one at negative pi over 2. But the tangent, we don't have this part if we have the absolute value, because the inverse cosh just starts at 1, so it's always positive. So keeping that always positive means we got to keep this always positive, means we got to keep this always positive. So we're only using this part of that tangent from 0 to pi for the secant, because it is the cosine. We have a vertical asymptote. Here's positive. This is negative. Now these are positive, but we're only using this part here. So I think we can see why the answer in the back says x has got to be between 0, because we can't make it 0, and pi over 2, because it's undefined there. Now you're going to have to do that every time you do some of these. I'm not sure I'll be that picky, but do recognize that there are some restrictions that we've placed on this from the beginning of the problem. The Cosh is always inverse, at least, is always going to be positive. The Cosh inverse, if you'll remember, starts at 1, sort of like the square root. So this has got to be positive. Whatever you do, it's got to be positive. Does that make sense? A little bit of sense? Okay, how about 48? Let's change colors. I'm sorry, 38. We want to verify that this is true. That the integral of x sec inverse of x dx is equal to x squared over 2 sec inverse x minus 1/2 the square root 1 minus x squared plus c. Well, the plus c comes because this is an indefinite integral, so that's true. The rest of this, though, we've got to figure out if the rest of it's true. And it's probably easier to call this y and show that the derivative is this x sec inverse x. So this is a product. We need the product rule. The derivative of the first, which is 2x over 2 times the second, sec inverse x, plus the first x squared over 2 times the derivative of sec inverse, which is the negative, because of that, see, oh, it's negative, because the sec is negative. Negative 1 over the square root, no, first x, square root of 1 minus x squared. That should be correct. I think I've got everything there. This is multiplication between. So this is just x sec inverse x. This one is negative x squared over 2x square root of 1 minus x squared. Okay, that's the derivative of the first times the second, plus the first times the derivative of the second. But I need also minus the derivative of this. Remember, this is 1, let's call this 1/2. 1 plus x squared to the 1/2. That's what we're thinking, at least. So it's 1/2 times 1/2, or 1/4. The 1 plus x squared, but now subtract 1, you get the negative 1/2 power, times the 2x, which is the derivative of what's inside. So this minus, and we have this negative square root in the denominator. We also have a 2x in the numerator and a 4 in the denominator. Hold it. So be careful, don't do what I just did and try to do this too quickly. We're subtracting this with the 1/2, but we're also multiplying by a negative 1, multiplying by the 1/2, I'm sorry. So you guys probably caught this. This is not plus. That's what's throwing me off. This is a minus. This is a minus. So this minus means that this is a negative 2x. So this negative and this negative make it a positive. That's what I was trying to do, is get rid of this, because I just wanted this first part for the x Cosh inverse x. So that's why I'm glad that happened. You stop for a second, you say, what's going on here? This isn't quite coming out the way it's supposed to. It's supposed to be just that. So you've already got that over here. These things, they got to cancel somehow. So dy dx is the x Cosh inverse x. Oh, the derivative also of a constant is 0. So this is now negative x, because this cancels one of those, over 2 square root 1 minus x squared, plus, this cancels that, and that makes that a 2, x over 2 square root of 1 minus x squared. And so these cancel, and you have just this thing. So we have verified that this is a true identity. Are you going to memorize that? No, of course not. I wouldn't, at least. Maybe you can. You might have a better idea of what to do with that. But I'm glad we caught this negatives, and I'm glad I made that mistake along the way. Another problem, number 48. We want to find the indefinite integral of the cosec squared of 5 minus x dx. Well, I like to do substitutions. Maybe you guys can see this, but for me, it just helps so I don't make silly mistakes like I did on the last one. If u equals the 5 minus x, then du is equal to a negative dx. I don't have a negative dx, so a negative du equals dx. So I'm going to rewrite this in negative outside. The cosec squared u du. Well, what is the antiderivative of cosec squared du? I guess this negative should go with that, because when you got the negative, it is the cosh u plus some constant c. But I don't want u. I want to replace that. And I get the cosh of 5 minus x plus some constant c. And it's a good thing I had that list, because I'm not sure I would have seen that, but I would have worried or wondered about it if that was true. Okay, that's number 48. How about another one? Number 58. We'll go by tens here. Let's see, now I've got a definite integral from 1 to 4 of 8 cosh square root of x over square root of x dx. So I'm going to do that again. Let u equal x to the 1/2 square root of x. Then du is equal to 1/2 x to the negative 1/2 dx, or 1 over 2 square root of x dx. Now I've got the dx and 1 over square root of x, but I don't have the 2, so I'm going to put the 2 here 2 times, both sides. So now this will be a 2. Don't know what the limits are yet. The 8 should also come outside, most likely. The cosh of u and the rest of this with the 2 and the du is that dx squared of x. So now I need these limits of integration. So at x equals 1, u equals. If x is 1, square root of 1 is 1. So I can start that at 1. At x equals 4, u is the square root of 4, or 2. So I can then change those limits, make this a little easier. 16 times, what's the antiderivative of cosh? Sinh. U from 1 to 2. So this is 16 sinh 2 minus sinh 1. How far can I take this? It all depends. That's one way of doing this. If you wanted to change it to exponentials, you could, but I'm not sure it gets any better. I forget what the back of the book said. Unless I tell you to change it, I wouldn't. Okay, so stop right there and go on to the next one. How about number 74? Let's change colors. We want to evaluate this 2 different ways. The first way is with inverse trig functions, and write your answer with an inverse trig. And then there are some approximations we can use to inverse trig functions. I guess there are different definitions, and then we can use that. But we're going to start with this from 1 to e dx over x times the square root of 1 plus ln x squared. So this looks like that one of those, but it's got an ln x. What do? Let u equal ln x. Then what is the derivative? Well, that's 1 over x times dx. Or, if you want to, put the dx over x, which is this part. Okay, so this becomes the du over just the square root of 1 plus u squared. Now, this was making me think that it was one of those sech or coseches, but it's not. Because of this substitution, it breaks it back down into just a sinh. Now, I do need limits. Let's see. At x equals 1, u is equal to ln 1. And u then, what is ln 1? That's 0. At x equals e, u is equal to ln e. Well, let's see. What power do we take e to get e? We just use 1. So the upper limit is 1. So this now becomes the antiderivative, and it's just the definition. The sinh inverse of u from 0 to 1, which is the sinh inverse of 1 minus the sinh inverse of 0. Do you remember what that looked like? Inverse sinh. 0 was 0. So this just becomes sinh inverse of 1. Now there's a way of writing this, I guess, with natural logs. The sinh inverse of 1, if you look at that formula, you get the natural log, this is part B, of 1 plus the square root of 1 squared plus 1. That's what the sinh can be. The natural log of x plus the square root of x squared plus 1, which equals the natural log of 1 plus the square root of 2. So this is another way you can write this same thing. These two are exactly the same. How do you check that? Well, let's see if we can do that with our calculator. What is the inverse sinh of 1? Let's get out of this, clear this stuff off. We need the inverse sinh. Go to the catalog, go to S, find the inverse sinh of 1. 0.88137357 because of the way this is defined. So what is then the natural log, ln, of 1 plus the square root of 2? Close the square root, close the natural log. Boy, it looks pretty much the same. Interesting. So, take some practice. Takes maybe a list of the derivatives and maybe the integrals too, of both the hyperbolic functions and the inverse hyperbolic functions. But I'll let you use those. So get one nicely written, get used to them. All the negatives that might be in there that aren't supposed to be where they're at because you're used to the regular trig functions. That's it for section 7.7.